his PhD at BU, working with Adam Smith. He's done great work in differential privacy, private estimation, and also memorization, understanding upper and lower bounds for memorization, which he'll tell us more about. So without further ado, the floor is yours.
All right, great, thank you. So yeah, so I'll be presenting work today based on two related papers. The most recent one is joint with Mark Bunn and Adam Smith. And the other paper is with Mark and Adam, along with Vitaly Feldman and Kunal Talwar. I don't know what the standard protocol is, but I'm happy if you interrupt me to ask questions at any point. Before I get into it, I'd just like to introduce myself a little, right? So for the first 2 years of my PhD, I was advised by Peter Chin, working on some applied machine learning problems, and then focusing on compressed sensing for neuroscience applications. Since then, I've been advised by Adam, and my research is focused on these two related lines. The first on the theory of example memorization that I'll talk today, and then also on private statistical estimation, which I'll hope to take a couple of minutes at the end of the talk and talk about some ongoing work that I'm excited about there. Okay, so we all know that machine learning models contain information about their training data. This is exactly the point. However, sometimes they contain a lot of information. In extreme cases, memorizing entire examples from their data. We'll see examples of this in a second. Our work shows that this example memorization behavior is, in general, unavoidable. We give natural settings where algorithms that are accurate must contain a huge amount of information about their training data, even if that information is irrelevant to the task at hand. Before we get into formal definitions, let's talk about what I mean by example memorization. The k-nearest neighbor classifier explicitly memorizes all of its data points. The classifier is, of course, just a description of the data set. One can imagine, and we'll see, that similar behavior might happen in other models implicitly. The word memorization is also used to refer to the distinct concept of label fitting or interpolation. This topic came to widespread attention with the work of Zhang et al., showing that large networks can fit random labels. And most relevant to our work is that of our collaborator, Vitaly Feldman, who showed that there are settings where high accuracy classifiers must fit the labels exactly. In contrast, our work is about memorizing the inputs themselves, the high dimensional samples. And we show that accurate models must somehow encode the data. Let's talk about why this might happen, and then I'll show you an example task on which such memorization is required. So high-dimensional data, such as images or text, contains both relevant and irrelevant information. Even if we, the algorithm designers, can't say exactly which is which, we hope that our training process will produce a model that distinguishes the two. We show that in a batch setting, when you receive the examples all at once, you can learn even when you can't distinguish what's relevant from irrelevant. However, for high accuracy, you must keep around essentially all the data because you don't know which parts will be useful. You can't just discard the irrelevant parts of the training data. In a streaming setting, such as one-pass stochastic gradient descent, we show that even if at the end of the stream you can learn exactly what's relevant and not, you must still memorize during the training process, requiring a lot of memory. Our work formalizes these concepts with simple and natural learning tasks, which for concreteness, I'll introduce one now. It's a multi-class classification problem on the hypercube. Examples have D binary features, and the labels are 1 through K. The task is just to identify which cluster generated that input. In each cluster here, each cluster will have a sparse set of fixed features, and all others will be filled in uniformly at random. This makes explicit this distinction between relevant and irrelevant information because these random features are useless for classification. A key idea in the proofs for this task is that with only a few samples from a cluster, you cannot reliably identify which features are fixed and which just appear to be fixed in your sample. And in particular, with only a single example from this cluster, the string just looks uniformly random. You have no idea about which features are fixed. So I'd like to invite you to think about this work from two different angles. The first is, of course, privacy. Example memorization can lead to catastrophic privacy violations. There's this well-known XKCD where the revolutionaries are foiled by autocomplete, but we'll see in a moment that this precise thing happens in practice. Beyond privacy, our work addresses fundamental questions about the theory of machine learning. For instance, we address natural questions in complexity theory about space and information requirements for learning. I'll also talk about how our work gives possible explanations for questions of why large neural networks succeed in practice. Okay, let me outline the rest of the talk. I'll talk a bit about some related work, and then the main section will be the two sections on the two papers. I'll then summarize with some future directions and talk about some ongoing work a little bit on private estimation. Let's start related work by talking about example memorization in practice. A clean example came in the form of this work by Carlini et al. On the secret sharer, where a canary sentence is inserted into training data, and the trained text generation models happily spit it back out. Later, a large group of authors showed that this type of behavior appears in GPT-2 and other similar text generation models without any modification to the training data. These models have memorized verbatim a huge amount of information, including news articles, random-looking strings, and most worryingly, personal information. Our paper does have some experiments, but appearing after our first paper, two works demonstrated reconstruction of training data from image classifiers. The first uses a strong adversary to extract who knows all but one of the data points, to extract that final data point from a trained CFAR10 classifier. We have the target images on top and the reconstructed images on the bottom. They're quite good, as you can see. The second recovers via a weaker adversary data from a network trained on small subsets of CFAR10, but the adversary doesn't have any strong prior information about the images. I think these results are quite interesting, and I look forward to seeing how these things evolve in practice. I'll also cover our experiments, which achieve strong reconstruction on synthetic data. Shifting gears, let's talk about some relevant theoretical work. There's a line of work on learners that use little information, studying upper and lower bounds on the information contained in models about the data set. The result most closely related to ours is work by Livni and Moran, who give limitations of the Pack-Bayes style of analysis. An implication of their theorem is a lower bound on information in the model of n times log d, where n is the number of examples and d is the dimension of the data. Our lower bound is n times d, which is a significant strengthening of that particular result of theirs. Another related concept is that of representation complexity. The representation dimension characterizes the sample complexity of pack learning under pure differential privacy. Roughly, representation complexity aims to quantify the information in a hypothesis or model about the task itself, while our focus is on the information in the model about the data itself. There are many papers studying trade-offs between samples and memory for learning in streaming settings. Some of the initial questions and answers came from work by Shamir and by Steinhardt, Valiant, and Wagner. But the area was kind of kicked off by work by Roz, which gave lower bounds for parity learning. This work has been extended and generalized in many different ways. When I introduce our results on streaming, I'll talk a little bit more about this area of work. Finally, there's a great deal of work on understanding why large-scale deep learning is so successful in practice. There's a a recent survey that goes over this in great detail. Three common hypotheses are that large networks are just simply more expressive, and this is the result for their success. That perhaps they facilitate easier or faster optimization, and perhaps that they have better generalization properties. Our work supplies a fourth, not mutually exclusive explanation. Models must memorize information whose relevance is not yet clear. We'll now move to talking about our batch results. In both this and the streaming section, we'll follow the same formula. I'll introduce the learning setting and state a general theorem, which will apply to multiple results. And then I'll describe the specific tasks that it applies to. And finally, we'll cover some proof ideas. And in this section, we'll also see the experiments that we've conducted to supplement our theorems. Okay. So our batch learning setup is simple, but not exactly standard. We have a data set X, which is n rows drawn IID from some distribution P. The data will have D bits in each example, and we'll have some labels that are either binary or multi-class. You can think of the data as being high dimensional, so the dimension may be at least as large as the number of samples. A note about this distribution P, we'll need it to itself be a random variable sampled beforehand from some prior or meta distribution Q. So before we draw the data, we'll sample P, and then we'll sample the data IID from P. We then feed the data to a learning algorithm, which outputs a classifier. I'll emphasize this learning algorithm has no restrictions on it. In particular, there's no kind of computational restrictions or anything like that. We evaluate the classifier in the usual way with a fresh test data point, and we judge it correct or incorrect. We'll call the error of the algorithm the probability of an incorrect classification over this whole process, the draw of the data distribution, the draw of the training and test data, and any coins of the algorithm. Our central question is, what does this classifier M tell us about the data set X? So we call this meta distribution Q the learning task because it kind of defines everything else about the problem. Q is known to the algorithm, but the distribution P will be a priori unknown. It will, in general, depend on N and D, which means the hard distribution is going to be tailored to the sample size in these results. For each task in this setup, there will be a Bayes optimal classifier that minimizes the misclassification error, but exposes lots of the training data by necessity. Before I state our theorem, I need to give a very important technical tool, which is defining Shannon's mutual information. That's how we're going to quantify information today. For random variables X and Y, we define their mutual information as the difference in the uncertainty about X minus the uncertainty about X after observing Y. Now, these are entropy terms. If you haven't seen entropy before, the definition is on the right-hand side. But it's not so important. You can just think of it as a measure of uncertainty in a random variable. It has a number of nice properties. For instance, it's symmetric, and X and Y are independent if and only if the mutual information is 0. We'll also define the conditional mutual information, which asks about the information between X and Y in the presence of some third observed random variable Z. Let's see how we use this term in our use case. So we've got data X, classifier M, and P, which is the data distribution, which is a random variable as well. We're going to care about the mutual information between X and M conditioned on P. To interpret this, consider an observer who knows the data distribution. How much does their uncertainty about the data reduce when they see the classifier? In other words, this mutual information between X and M conditioned on P quantifies information that's unique to the data set and unrelated to the task, because an observer who knows the data distribution didn't know that information about X before they saw the classifier. In other words, this quantity captures irrelevant information that's been memorized about the data set. So let's look at our main theorem. There's a natural task Q such that for every learning algorithm with error within 10% of optimal, this mutual information between X and M conditioned on P is big omega of N times D. And since the data set itself only has N times D bits in it, this means that M must memorize a constant fraction of the information in the data. And furthermore, it must memorize that much irrelevant information. To emphasize the notation here, little p is a problem instance, a distribution on labeled examples. Capital P is a random variable chosen from this meta distribution. And opt is this best possible average error, the Bayes optimal error for the task. For some of our tasks, we're able to prove even stronger bounds qualitatively. For some, we'll establish that there is a large subset of points, which we'll call S, some special examples. And this S will itself have a lot of information in it. Its entropy will be a constant fraction of the entire data set. We prove that there are natural tasks such that for every learning algorithm with error within epsilon of optimal, the mutual information between this subset S and the classifier approaches the entire amount of information in S. So we have this 1 minus f of epsilon term. F of epsilon goes to 0 as epsilon goes to 0. So that means as the error of the algorithm approaches optimal, the classifier must contain entire examples. Think full addresses or phone numbers. So these two informal theorems are the main results from this first paper. Somebody's raised a hand.
Yes. So I have a question here.
Yeah.
You mentioned there's a large subset of points S. So can you like maybe comment or explain what does large mean? Is it like a fraction or is it just by mutual information large?
It's large. It's going to be like a third of the data set in these distributions. A large constant fraction of the data points will belong to this subset S.
So it doesn't matter whether these points are duplicates of the sum of the data points in X.
That will matter, yeah. So in a second, we'll talk about what actually this S is because it's very important in our proofs, of course.
Okay, thank you very much.
Yeah. Another question?
A quick question. So why is the information called irrelevant?
Yes. So for instance, this first theorem where we say that the mutual information between X and M conditioned on P is big omega of N times D. So we say that this talks about the irrelevant information that M is memorized. Because in some sense, X may have some information that's useful for the task. That information is about P. So it's somehow like about the data distribution, or learning it tells you something about the data distribution. There's other information where learning that information tells you nothing about the data distribution, and we call this irrelevant. Because we measure mutual information conditioned on P, we think about an observer who knows the data distribution, and we ask, how does their uncertainty about the data reduce when they see the classifier? So it's things that somebody who knows the data distribution didn't know about the data. It's information that's unique to the data and useless for the task. Does that kind of answer your question?
Yeah, thanks.
Cool, thanks. Another question?
Hi, can I ask a question? So like I have one question about like this Bayesian assumption you made. So if I understand correctly, the left-hand side is the average, right? So there exists one distribution that achieves something like this lower bound, right?
Yeah.
So I basically missed that part that you go to Bayesian setting, and what is the necessity of that? This is the first question. Like the second question is, so I'm trying to like to put this result in context. For example, this learner that used little information, or this result by Shai and Roy, they show that there is such scenarios that the mutual information is lower bounded, but the classifier is good, right? So can you also compare this, what the implication of this result with those results? Thank you.
Yeah, both great questions. So this kind of like assumption that there's a prior over the data distribution helps us prove our result. It also implies like a minimax style result, which says for any algorithm, there exists a single distribution, which causes it to have high information with the data. So it's kind of just like a simplifying assumption for us, but it's still, we think, just as strong in terms of the implication. Because even if I tell you exactly what the prior over data distributions, you still can't avoid.
Mm-hmm.
In terms of comparing to results, and I won't be able to compare to everything, but I think the one fundamental difference that's important here is in this work, the hard distribution is tailored to the sample size. So, and we'll see that why that's critical to achieve such strong results. For these tasks, if I fix the distribution and let n grow, even kind of like n log n or something like, or even like a log time smaller or larger, then you can get away without memorizing much information, without memorizing a lot.
Okay. Thank you.
Yeah. We'll hopefully see some examples of exactly why this works in a couple of minutes. Okay, great questions. Anything else? Awesome. Okay, so yeah, so let's look at what these tasks actually look like. So like the example I showed, there'll be mixtures of many clusters. Each task Q is a meta distribution or prior over problem instances, where each problem instance is defined by a mixture over these subpopulations and a data generating distribution, P sub j, for each subpopulation j. So these P sub j's are going to set the subpopulation's particular rules for classification or the label. I'll note that this subpopulation structure descends directly from the work that I mentioned before by Vitaly Feldman. To specify the task Q, we need to provide a distribution over the mixture weights, which can always be uniform, that's fine. And we need to specify some distribution Q task over the subpopulation instances. So for each subpopulation, we'll sample this PJ IID from this Q task distribution. Just to make it explicit, this Q task will generate the distributions for each subpopulation. Now let's look at what these per subpopulation distributions actually look like for our two central tasks. The first one is this hypercube clusters task, which is what I described before. Each subpopulation distribution is described by a sparse set of fixed features, each of which is chosen to be fixed with some small probability rho. The bits are picked to be either 0 or 1 uniformly at random. To generate a labeled example from this distribution, we just fill in all the other bits uniformly at random, and the label is the cluster name, J. This results in samples appearing biased together. And you can see once you receive, say, like log D samples, then you can learn the fixed bits exactly. But with fewer samples, you won't be able to. This first distribution is supposed to abstract any kind of high-dimensional image classification task, like or high-dimensional multi-class classification task, like image classification. The next task, which we call next symbol prediction, is meant to abstract any kind of sequence prediction task. So here, each subpopulation is defined by some randomly chosen reference string C and a noise parameter delta. To generate labeled examples from the distribution, we generate a random length L and then produce a noisy prefix from the reference string of length L. The label is just the next bit of the reference string. So these samples are corrupted prefixes of this reference string. And again, you can see once you have enough samples from the subpopulation, you'll be able to learn the reference string to high accuracy. But with only a few samples, you'll still have a lot of uncertainty. And in fact, we can show you need to memorize. So these are the two main tasks that we work with in this first paper. Let's look at what how the proof goes at a high level. So I mentioned we have this special set of examples S. We'll call these the singleton examples. They are the sole representative of their subpopulation. So the first step of the proof is to show that there will be many singletons in the data. This is basically by construction. Now you notice if I fix the distribution and let the sample size grow, then I'll eventually have very few singletons. And so this is why we really need the hard distribution to be tailored to the sample size. And for instance, it's not like there's, there is something special about these examples S. Next, we show that if you're near optimal overall, you must be near optimal when the test example comes from a singleton subpopulation. This is because they form a large mass of a large part of the probability distribution. Then we apply information complexity lower bounds, showing that you must reveal near complete information about the singletons. This is the kind of hard step we need to prove new information complexity lower bounds. Let's look at what one of these lower bounds looks like for this cluster labeling task. Recall each feature is chosen to be fixed with some small probability row. We're going to use a lower bound for the following one-way communication game between Alice and Bob. We call it the singletons only game. Alice is going to get k singletons from the data set, and where each one is drawn from its own cluster. And then Bob is going to get a sample from one of those clusters, and his job is to guess which one. Alice gets to send Bob a message, which you should think of as corresponding to the model in the real learning problem. The first step of our proof is to show that this is equivalent to a much simpler and cleaner game. Equivalently, we can think of Alice as getting k uniformly random strings, and Bob as getting a noisy version of one of those strings, and it's his job to guess which one. We can think of Bob's sample as being run through a binary symmetric channel, a very noisy copy of one of Alice's inputs. So as a corollary to this, Alice and Bob's best strategy for this singletons only game solves nearest neighbor. Note that the noise level on the binary symmetric channel row exactly corresponds to the probability of a feature being fixed. We then prove lower bounds for this nearest neighbor problem, that if Bob succeeds with probability close to optimal, then Alice must reveal in her message a large constant fraction of the information she received about her data set, about her singletons. The proof uses a strong data processing inequality, analogous to its use in a paper by Hadar et al. Proving lower bounds for the gap Hamming problem, which is a classic problem in communication complexity. Basically, this strong data processing inequality says that data is in fact destroyed when you run a sample through this binary symmetric channel. We conjecture that this theorem can actually be improved so that instead of a 1 over 2 ln 2, we have just a 1. This conjecture would imply that this kind of memorize entire examples interpretation. As it is, we currently just have to memorize a large constant fraction of entire examples. Okay, so our proofs are just information theoretic and don't explicitly say that once you have a classifier, you can extract that information. So to supplement them, we'll do some experiments. We'll generate data from the hypercube clusters learning task, where each subpopulation has a single label. And we'll train multi-class logistic regression and multi-layer perceptron models on it. We'll give an adversary query access to the trained model. And we'll also tell them label J was a singleton. It's kind of side information to make things cleaner. The adversary, in this case, is just going to do something very simple. It's just going to, for instance, maximize the probability that the classifier gives to label J, find some X that the classifier really thinks comes from label J. we'll visualize how this model accuracy and the adversary success evolve over the training process. So in our experimental setup, the data set will have 500 examples, each of which has 1,000 features, and we'll set roughly 25% of those bits of those features to be fixed. And we'll just train with vanilla gradient descent. I'll spoil it and say in both cases, both logistic regression and the neural network, we're able to recover over 98% of the singletons bits, almost perfect recovery from these trained models. Here are our results for multi-class logistic regression. On the x-axis, we have the gradient steps over training, and on the y-axis, we have the errors. I should mention these errors are rescaled so they live on the same scale, but we have the full details in the paper. For now, you can just kind of interpret them visually. The train and test error quickly go down to 0, but the interesting thing is this attack error. The attacker starts out very bad and almost linearly decreases over training until, in the end, the attacker is recovering all of the singletons bits from this trained logistic regression model. The story for the multi-layer perceptron with a single hidden layer is basically the same. The train and test error are now a little funky, but the attack error is monotonically decreasing. Every gradient step, the attack gets a little bit better until it's recovering almost all of the bits from the singletons in the training data. I want to mention one other neat empirical result. This is a plot of the neural network attack error, as before, along with its test error, but only on the singleton subpopulations. As you can see, eventually it does well on these subpopulations on the right-hand side, but for a while it has 0 accuracy. So for instance, after 750 gradient steps at this blue line, the algorithm has memorized almost all of the bits in the singleton examples and will gladly spit it back out to an adversary. But the network doesn't know how to use the information that it's memorized. It still has 0 error on these singleton subpopulations. As a little empirical oddity, I find it quite interesting. Okay, so this is that's the end of the setting, the batch setting. We'll now talk about streaming, and again, we'll follow the same formula. We'll introduce the setting, give a general theorem, and then describe specific tasks that it applies to, and cover some ideas from the proof. Okay, so we want to deal with learners who work in the streaming setting, a setting such as stochastic gradient descent. Like before, we'll have d-bit data points with n data points, each of which are drawn IID from some distribution P. After receiving each example, the learner will update its memory state from M1 to M2 all the way to the end. Crucially, these intermediate states need not be classifiers. They can be arbitrary. They don't need to make predictions or anything. After receiving the final example, the algorithm will output a classifier and we'll evaluate it in the same way with a fresh data point. We'll call the space usage of the algorithm the maximum in bits of the description of any of these memory states, where the max is taken over T and any randomness in the data or the algorithm. Our goal is to understand space as a function of the data dimension, this parameter kappa, which will capture the size of a good classifier. This will become clear in a little bit. We're dealing with hypothesis classes, so we'll have a size for each element of the hypothesis class. And n, the string length, is the other parameter we'll care about. Our main result says that there are natural hypothesis classes for which non-trivial prediction requires space d times kappa over n. Let's unpack this a bit. By non-trivial prediction, I mean just having a constant error above random guessing, constant advantage above random guessing. And because kappa is the size of a good classifier, by uniform convergence, roughly kappa examples suffice to accurately learn this hypothesis class. So this factor of kappa over n is the minimum number of samples divided by the stream length. it starts at 1 and goes down as n grows. And then this d times kappa is the size of the smallest data set necessary for learning. So our lower bound matches that data set size and then decreases as the string length grows. We can kind of visualize these results and compare them with prior work. So I mentioned this work by Roz, which proves lower bounds for parity learning, where the example is d bits, and the label is the parity of an unknown subset. So this is a simple problem that can be solved with Gaussian elimination, but to do that, you need kappa times d memory. Roz proved that you need kappa times d memory for any string length up until exponentially large, when basically you can do guess and check. So this is a very strong lower bound that applies across a wide string length. Later work, independently by Sharon, Sidford, and Valiant, and Dagan, Kur, and Shamir, proved strong lower bounds for linear regression, again, requiring kappa times d memory. However, these lower bounds only hold for a very narrow range of string lengths. I put it here as like log 1 over epsilon. I want to note that this is just a kind of an upper bound informally. What they prove is slightly weaker. So this green line is like the strongest possible thing you could prove about linear regression. Our work is represented by the blue line. At small stream lengths, we have a large memory requirement. And as n grows, it decreases smoothly, applying across a large polynomial-sized set of samples. Okay, so our theorem talks about space, but of course, I'm speaking today mainly about memorization. So I'm going to talk about why this theorem or our results also imply memorization. Our proofs use a particular notion of information cost, recently introduced in Braverman, Garg, and Woodruff. I'll defer the full definition for a couple slides, but it's a sum of terms that look like this. It's the information between the tth memory state and the ith input, conditioned on the immediately preceding memory state and the parameters of the data distribution. So as a corollary of our results, not a corollary of the space result, but an intermediate theorem, on average over time steps, the mutual information between the tth memory state and all the preceding data points, even conditioned on the distribution, is big omega of d times kappa over n. Thus, for short streams, when the sample size is approximately kappa, the average memory state must remember omega of d bits about a constant fraction of all the inputs. And this holds even though at the end of the stream, the algorithm can have a much smaller memory size, just kappa. Okay, so let's talk about our tasks. We want to prove lower bounds for hypothesis classes that feel like the models used by practical machine learning today. So here are 3 of the classes we consider. The first is multi-class sparse linear classifiers. There are k labels, and the hypotheses are just argmaxes over k hyperplanes, where each hyperplane is log k sparse. So by specifying that the hypotheses are sparse, this specifies this kappa parameter, saying that each hypothesis has a small representation. By replacing this max with a softmax, we can do multi-class sparse logistic regression. The second hypothesis class is sparse linear classification over degree 2 polynomial features. Here, the labels are binary, and the classifiers are linear in a polynomial feature space, where each feature is a degree at most 2 monomial in the original data point, in the original data. And we ask that the classifying hyperplane is k sparse. Our final task is a regression problem for one hidden layer neural networks, where there are k hidden nodes, and each node has at most log k wires coming into that node. So, to restate, for each of these problems, even though the final classifier is itself small, we prove lower bounds that depend on the ambient dimension of the feature space, much larger than this kappa parameter. Okay, let's talk about the proof. We establish a series of reductions. We use a learner for one of the hypothesis classes to solve a distributional problem that's defined in a familiar way as a mixture over k subpopulations. This is not the same distribution, but it's closely related to the hypercube cluster labeling task. We then consider solving a single subpopulation version of this task, where the learner is given a stream, each of which has d bits in each entry. And the learner is asked to distinguish whether that stream has a few fixed indices versus all of the elements being random at every point. Our final reduction is even simpler. The learner must determine whether a stream of d bits is random or fixed to all ones. This is quite a simple problem, but it's the kind of the base upon which we build our proof. These last two works are similar to hard problems that appeared in prior work by Shamir and Braverman, Gargan, Woodruff, but we need to prove slightly different versions of them using slightly different techniques. The fundamental trick going on in this proof is we're embedding in each hypothesis class this mixture of k subpopulations, even though it's not clear on the face of the hypothesis class that there's a subpopulation thing going on. This is a new approach that allows us to move beyond just distributional results into concrete hypothesis classes that really look like the hypothesis classes we're used to dealing with in practice. Okay, so the main tool that we use to prove our lower bounds in this section is called composable information cost. As I mentioned before, it's a sum of terms about memory states conditioned on and previous data points. We have a sum over all memory states and a sum over all preceding time steps. We modify their definition to condition on P, which makes everything easier for us and also admits this memorization result. It's useful for us in two ways. The first is that a lower bound on this term gives a lower bound on the space usage, so we can use it to prove space lower bounds. And furthermore, it's useful for direct sum arguments. In a direct sum type argument, you want to argue that solving simultaneously k copies of a single problem is at least k times as hard as solving a single version of that same problem. We actually use this type of argument in two different places in our proof. And although I won't have time to illustrate it, I'll mention that this composable information cost is very useful for proving these types of, for establishing these types of results in streaming settings. To finish this section, I'll say a word about our lower bound for this 1-bit task, which is a kind of interesting lower bound. So again, the learner is asked to distinguish whether or not the stream it's given is uniformly random or fixed to all ones, just a 1-bit stream. So it's trivial to establish that this takes 1 bit of memory. This is a very easy task. You don't need to work hard. However, it's non-trivial to get a lower bound on this composable information cost. And this was actually surprising to us when we wrote it down because we thought it would take 2 minutes to prove it. But what's going on here is that because we're conditioning on the parameters of the data distribution, we're really conditioning on whether the stream is fixed or uniform. So this claim says that the algorithm must memorize a constant fraction of a bit of information, a constant amount of information about the stream, even conditioned on the stream itself being uniform. So this is actually a non-trivial thing to establish. In the proof itself, we set up a Bayesian observer who sees the algorithm state. And so, Reverend Bayes has a belief about whether or not the stream is fixed. These posteriors form a random process, P0, P1, all the way through Pn. And it's this random process that we analyze in our proof. So the prior belief starts out at 1/2 because it's uniform either way, which the stream could be. And then on average, we showed that this posterior process must decrease by a constant amount. This is because the algorithm is itself accurate. So the Bayesian has only better accuracy than that. And then in the proof, we connect these gaps between when the posterior decreases to revealing information about the underlying stream. Kind of a neat little proof for a neat little, surprisingly non-trivial problem. Okay, so I'd like to now spend a little time summarizing what I've done and then talking a little bit about in-progress work. So we saw how intuitively you must memorize when you can't identify the relevant information. We talked about, we hope that the model can learn to distinguish relevant from irrelevant, but when you can't, you may have to keep everything around, even if you can learn. We also talked in the streaming setting, like stochastic gradient descent, how even when you can, at the end of the stream, distinguish relevant from irrelevant, you may still be required to memorize during the training process. We saw a few simple examples, including this one of classifying clusters on the hypercube, where in this example, if you only have a few samples, you cannot identify which features are relevant and which are irrelevant to the task. We saw a couple of informal theorems. We saw this one in the batch setting, where there are natural tasks that require memorizing a constant fraction of irrelevant information in the data. We saw a stronger result about memorizing entire examples. And we also saw some experiments about reconstruction in practice on simple models and synthetic data. We saw a lower bound for the streaming setting, where we have any natural hypothesis classes like linear models, for which non-trivial prediction requires space d times kappa over n. We talked about how this matched the natural upper bound of storing the data set, and the lower bound decreases as the sample size increases. We compared this to some other results and also talked about how we also showed that the algorithm must memorize during the stream. We talked about some implications and how this work suggests that maybe we can't avoid this type of memorization behavior in general. And we also, going hand in hand with that, suggest an alternative explanation for why large neural networks succeed in practice. Not only perhaps it allows for better optimization, but neural networks must memorize information whose relevance is not yet clear in the training process. This holds even if at the end of training, you can produce a neural network that's much smaller, you may still require a large space during training. Of course, the space follows because to memorize a lot of information, you need a large network. I'd like to suggest a few directions for future work. The first is quite natural, are there learning problems where reconstruction is provably required? Can I produce a theorem that says there exists a natural task such that for any learning algorithm, there is an adversary who's able to produce a data set that looks quite like X in some specific way? The next question is, hand in hand with that, is can we produce stronger practical attacks? So there are a couple existing results, each of which help the adversary in some way. I suspect that there are much stronger attacks that exist in practice, and we just don't know how to get our hands on the information that's inside the neural networks. And additionally, I think it's quite interesting to think about additional types of memory sample trade-offs in streaming. I showed 3 examples, one this strong parity learning result in red, a green result in linear regression, which applies only over a log scale, and our result in blue, which is a smooth decrease of 1 over n. But a natural question is like, what lives between the blue and red curves? What types of problems facilitate other types of trade-offs? And like, furthermore, if nothing lives between the blue and red curves, that in itself is also quite fascinating. So I think there are a lot of very interesting questions in this memory sample streaming area. So finally, I'd like to just take a couple of minutes and talk about some of my in-progress work on private statistical estimation. So this slide is going to be based on joint work that appeared at NeurIPS with Marco Gavilardi, Adam Smith, Jonathan Ullman, and Lydia Zakanthinu. So the task is Gaussian mean estimation in Mahalanobis distance under differential privacy. So given n IID samples from a d-dimensional Gaussian with mean mu and covariance sigma, where mu and sigma are totally unknown, we want to output an estimate mu hat that is close to the true mean in Mahalanobis distance. So we measure accuracy using this notion of Mahalanobis distance, which is actually quite familiar. This expression, the square of this expression, shows up in the PDF of the multivariate Gaussian. And it's the natural measure of distance for general Gaussians. It's affine invariant, and it exactly captures this idea that we want our estimate to have smaller error in the, quote, smaller dimensions of the smaller directions of the distribution. If we can represent our PDF with this like blue ellipse, this Mahalanobis guarantee says we want our estimate to be in this smaller alpha ellipse around the mean. Without privacy, we can use the empirical mean. And if the number of samples is roughly greater than d over alpha squared, then the true mean will be within alpha Mahalanobis distance of the empirical mean with high constant probability. Prior private algorithms for this task needed either d to the 3/2 samples or require strong prior information. Our contribution is differentially private algorithms that require no prior information about mu and sigma and need only roughly d over alpha squared samples for moderate values of the privacy parameters. This work gives two sample efficient but exponential time algorithms, leaving open the natural question of whether or not we can achieve the same guarantees in polynomial time. This is the question that's been occupying me for the past while. So I'll talk about this approach, which I think is promising, but I want to emphasize is not a theorem and is not fully worked out. A core step of one of our algorithms can be stated as follows. Given the input data set X, find a data set X tilde that's close in Hamming distance and has no outliers for some specific notion of outliers. We can think of it as projecting in Hamming distance our input X to some nearby X tilde into this set of blue no outlier data sets. And then our algorithm from the previous paper releases a noisy mean estimate, where from the Gaussian distribution that has mean, the empirical mean of X tilde, and has covariance, that's the empirical covariance of X tilde. Okay, so it's based on these estimates. There's other things that go into the algorithm, but that's one of the core steps. This actually has a quite similar form to robust statistics applications of what's called the sum of squares paradigm. A somewhat canonical example is some mean estimation problems, which you can kind of solve with the same thing. You take an input X and you find a nearby X tilde that, say, has small covariance. And then you release a mean based on that's estimated from that projected data set, X tilde. So sum of squares is a framework for producing and reasoning about convex relaxations. It's used beyond statistics, but it's resulted in numerous breakthroughs in robust statistics in the past 8 years. And it's been recently used in 2 papers for private estimation, work by Hopkins, Kamath, and Majid, and by Kothari, Monarangsi, and Valinker. And we'll see, this list is going to grow quite a bit in the next few years, I strongly suspect. A really interesting thing is that here, even though these tools from robust statistics, they may help us establish privacy, even if robustness isn't our goal. And so I'm interested in further understanding these connections between these two groups of these two bodies of literature as they pertain to high dimensional statistics. So with that, I'd like to leave you with our main intuition in the future directions. Thank you very much for listening to my talk, and I'm happy to take any questions. Yeah.
If there are any questions.
Okay. Nice talk, Gavin. I was wondering, like, if anything is known for like multipass streams, like if you're allowed to pass the stream multiple times.
Yeah, good question. So yes, our results are like our hard distribution cannot prove lower bounds for multipass streams. If I give you 2 passes, you can do much better with lower memory. There are some results. So there are at least 2 results for multiple passes. One by, I think, by Garg, Rosenthal for parity learning type problems. And then there's another result by Dagan and Shamir studying the memory complexity of detecting correlations in data. This is one that I didn't explicitly call out, but it has a very nice multiple pass interpretation for detecting kind of like weak correlations between data points. Yeah, and the dependence on the number of passes is kind of like exactly like what you would expect, that like having a data set of size 2n is just as good as having 2 passes over a data set of size n. There's another question from Amsterdam.
Hello, thanks for the talk. So one of the questions I had is about, so you have a distribution, your hard distribution depends on the data set size n, and the reason being that you need to have these singletons, which is obviously very sensitive to n. Do you think it's possible to relax that a little bit? Like, could I have the one distribution that works for a range of n that's like a constant factor, like anywhere between n and 2n, this would work?
Yes, so, okay, so yeah, maybe I undersold the result. It'll still work for n and 2n in terms of like, you'll have a constant amount of memorization, because if I throw 2n balls into n bends, I'll still have a constant fraction of the bends be singletons.
But like, what about n versus n squared?
N versus n squared is a very good question. I see like no reason that you know, that memorization shouldn't be required there. I don't know how to prove it. There are some other upper bounds that show, at least in some, for like average case learning settings. This is work by certainly by Yehudayov is one author that